my name is Emmanuel. I'm from the Cornell database group. So we are generally looking into how to make data more accessible, and voice interfaces definitely qualify for that. All right. So in the next hour or so, I'm going to tell you a little bit about what we have been doing recently with regards to voice interfaces. I'm going to give you a short introduction to voice querying and what that looks like. And I'm going to give you a little introduction to a prototype that I'm also going to present here. I'm going to tell you how we translate speech input into queries, basically how we understand what the user wants from us, and also how we get across the result to the user via a voice description. And then I'm also going to talk about how we can do all of those things in an efficient manner. All right. Then we're going to have a demo. And afterwards you can ask questions, but you can also ask questions during the talk. So I will explain whatever we find, whatever content we have on the slides. If I don't succeed and things are unclear, then please do ask questions, or more in general, if anything is unclear, please always feel free to interrupt me and ask. Okay? Good. All right. So you have probably already noticed that voice interfaces are becoming more and more popular. There's nowadays devices like Google Home or Amazon Echo, which are primarily targeted at voice-based interaction. And essentially every major computer company has nowadays virtual assistants that you can talk to, such as Amazon Alexa, Google Assistant, Apple Siri, Microsoft Cortana. Those are only some of the examples. Now, some of the reasons why voice interfaces are popular is that, first of all, many users perceive them as a very natural form of communication, because voice communication is pretty much the first thing that we learn. You can also use them from a distance, or you can use your Amazon Alexa, for instance, from across the living room, and you can use them by doing other things like driving, for instance. And most importantly, if you support voice interfaces, it broadens the user base, because there is users who cannot use traditional interfaces, and their voice interfaces seem like a very attractive alternative. All right, so this is why we have been looking into how we can bring those advantages of voice interfaces to the domain of data analysis. So we want to create systems that essentially listen to you, to the user. You formulate to the system queries, meaning you describe which data you're interested in, and then the system answers by a concise description of that data, summarizing the most interesting high-level tendencies. All right. Now, we have been working on this topic since a little bit. So here we have an overview of some of the recent papers starting in 2017. We have started looking into how we can enable voice querying on relatively small data sets. Then we have expanded that to larger data sets, and we have been looking how we can extend scenarios where the system only needs to support one single user to scenarios where many users need to be supported. If I want to make, for instance, the NYC Open Data accessible to a broad user base, then we need systems which can do this efficiently. All right. Now, in this talk, I'm going to focus on our latest work in that space, and this is also what I'm going to quickly demo here. Now, in following, I'm going to tell you at a relatively high level how that approach works, but please feel free to ask more questions either during the talk or also come and talk to me after the presentation. All right. So, the user might say something such as, give me some statistics on visual impairment in Brooklyn to us. And then the first thing that we need to do is to understand what the user is referring to. And that is already quite challenging, of course, because first of all, we need to have speech recognition in order to translate what the user tells us into text. And furthermore, we need to translate this input text into a more formal description, which tells us which data the user is actually interested in. So for instance, that entails identifying things such as that the user is looking for data on visual impairment here, or that we're looking specifically for data about Brooklyn. All of this corresponds to a subset of the data that we currently have in our database. So this is what we need to do in order to understand what the user wants from us. The final step is that we map the speech input to a subset of our data set. So let us assume, for instance, that in our data we have one large table which has columns, for instance, for indicating the borough, the neighborhood, the type of disability, as well as the age group. And this input query then translates into restrictions on those columns. For instance, we restrict the borough to Brooklyn, and we restrict the type of disability to visual. And for the user, all the rows are interesting, which satisfy all of those conditions. In this small-scale example, that would only be one single row, which talks about Brooklyn and about visual disabilities. After we do this, we get some subset of the data that seems relevant to the current query. Now, this might actually be a large table containing many rows. So we cannot just go ahead and just read out one row after the other one to the user, because people would be simply overwhelmed. So what we need to do is to somehow find the most important high-level tendencies in the data and summarize them via voice output. Now, for instance, if we consider this table here, we could choose to talk about some more specific facts, such as the ratio of the population who has a visual disability in Kennedy and among the adult population. Or we can talk about specific Kensington or East New York, for instance, or we can choose to talk about more generic facts, for instance, about children in general, or about larger geographic area, such as northern Brooklyn. So there's many possibilities about what I could tell the user. And the first question is, how many of them can we select in a typical speech? Now, we made a couple of user studies on this, where we essentially played users a speech description with a couple of facts, and then we asked users immediately afterwards to remember what we told them. And then we measured the percentage of facts that users recalled correctly. Now, here you see a plot where on the x-axis you have the speech length, which means the number of facts that we transmitted to the user, and on the y-axis you have the percentage of facts that they recalled. Now, the precise numbers are perhaps less important, but if you look at the behavior, you see that there's a very steep drop at over 3 facts. So probably we should restrict our output to something like 3 or 4 facts. It also depends on a couple of other properties, for instance, how detailed those facts are that we are transmitting, or even if we have numbers in our facts, it depends on how many digits we tell the user about for each of those numbers. So all of those things influence how the users can recall speech output, but still, for more than 3 facts, it's becoming difficult. So we have to be very selective about which facts we want to select for a speech output. And we need some kind of model which tells us what the optimal speech sounds like. Now, we generally assume the following model. We assume that users initially have some kind of expectations about data. Now, those expectations are probably somewhat distant from the actual data, so there is a mismatch between expectations and the actual data. Now, our goal when selecting speech output is to essentially change the expectations of the user such that the distance between the actual data and what the user thinks of the data decreases. So by selecting the right things to say, the most relevant things to say, we hope that we can somehow get users a better impression about what the actual data would look like. All right. Now, this model that I have just described, figuring out if I say this to users, then this is what users think, that is already a very interesting subproblem in itself. We also made some user studies on this, And of course, our model is simplifying, but at the same time, we made experiments to verify that if you select speeches according to that model, then users are better at estimating parts of the data than if you play them speeches generated according to different models. Now, assuming that we have a model which evaluates speeches in terms of how informative they are, what we could do is to simply try out different fact combinations and then generate speeches and then evaluate them, then finally retain the optimal speech, and this is what we tell the user. That works in principle, but it doesn't really work in practice. If you would do this, and we did that, you would quite often have something which takes minutes. And having a dialogue with that system would be like having a dialogue with somebody who likes to think for a couple of minutes before answering, and that will require a lot of patience. So we want to go away from that. We want to be better than that. And we have tried out quite a few different techniques in order to get there. We have in particular tried 3 techniques recently. We can first of all use approximate processing. So we don't work with precise results, but with some kind of approximation. We can use incremental processing, or we can use pre-processing. I'm going to say a little bit on a high level about those 3 things. So for approximate processing, it essentially just means that instead of operating on the entire data, we select a subset of the rows and then we work with that subset. Which makes things very fast, granted. On the other side, the problem is if you only work with a subset of rows, there is a risk that you're missing the rows that are most important. So this is kind of unreliable. Now, in the first approach people would think of, we'll probably think of something like this, is shown on this slide. There's a first phase in which the system is processing data and figuring out what speech to make. And then there's a second phase in which the system speaks the generated speech. And this means that you have to wait as user until speaking starts, until the entire speech has been generated. Now, that can be quite a long waiting time, as discussed before. So what we try to instead is to decompose the generation of a speech into many small processing steps. So in each processing step, we'll just generate the next fragment of our speech. And that means we can already start speaking if only the first fragment of the speech has been generated. And then while the system is speaking in the background, it is at the same time calculating in order to figure out the next speech fragment. So we're essentially overlapping speaking time with processing time, and the system will make up the speech as it goes along. Now, here we have significantly reduced the time that users need to wait until speaking starts. So in that sense, it is effective. At least as long as we consider one single user for which we can reserve the resources of the entire system. But if we have now a scenario in which just a system runs in a cloud computing platform and needs to serve many hundreds or even thousands of users, then this approach actually wouldn't really help, because it does not reduce the total amount of processing overheads that it has. It's just a little bit smarter about when it does the processing, right? So again, we have the same overheads as with the original method, which doesn't really help if I want to scale up large user groups. Now, what we are doing in the newest version is pre-processing, which means that before runtime, we have one long pre-processing phase where we kind of try to summarize the data specifically for voice output. So in a way, we are trying to answer most of the queries already in advance, at least at a relatively high level. We reduce the size of the data set by throwing away everything for which we know that it won't be relevant for generating voice output. This is what we do before runtime, and at runtime we have a very small synopsis of our original data, much smaller than the original data, and then if users issue speech queries, we simply look up the most interesting tendencies for that query in the previously generated data set. Now, the bad news is that preprocessing takes actually a long time. It takes several hours already for most data sets you should be able to finish within several hours on a reasonable server, let's say. That's quite a lot of time, but the good news is it doesn't really matter because we only have to do it once. And it's exchanged at one time in order to answer user queries. We just need to look up a couple of tendencies in our synopsis, and that should be very fast. All right. Now, before I come to the demo, is there any questions around the general principle?
I'm curious about the scale of the data, like how many records, for example, do you have?
How many records? Okay. Well, I mean, we tried with many different data sets. I'm going to present two data sets today, one rather small one with about 600, it's about 1 gigabyte, and it has something like 80,000 rows and something like 113 columns, I believe. So that one is already of a reasonable size, I would say, yes.
Now, for the pre-processing that you're doing, if you were to get a query that doesn't match anything that you've pre-processed, then you're stuck back with the first solution, right? Where you have to kind of take the entire thing, break it down, and process it before you output the data.
So in that case, we would never go back to the first solution because it just doesn't scale. What we'll do in this case is try to compose something which comes close to the query that you're interested in. So we have generated tendencies which might concern some data subsets which are not precisely the query that you're interested in, but they overlap with the query. So even in those cases, the system would still do its best in order to figure out what comes closest to the query. Yeah. But having said that, you can influence the pre-processing overheads, so you can, if you invest enough pre-processing time, you can be reasonably sure that all the queries are covered. It's very efficient at batching together different queries, so the processing time doesn't increase proportionally to the number of queries you generate. Okay. Yeah? We're doing that batch processing. Another thing that helps in that context, when using a voice interface, the queries that you can formulate reasonably are significantly simpler than the queries that you could write in a formal language or that you could generally write on a screen.
Sorry, can you say that one more time?
So if you write queries using a formal language or even an actual query interface, then you have time to stop and to think about things. You can reread what you have just wrote before. So you are able to formulate a relatively complex query. But when speaking things, and at least in our user studies so far, people use relatively simple queries, just because speaking a very complex query becomes at some point infeasible.
Yeah.
Right? And so for those queries that we received in our user studies, this pre-processing actually enabled us to train. Okay. Good. Right, it needs a little bit to start up. Okay, Google, talk to NYC Open Data. Let's start up. All right. So perhaps I should say a little bit more about the general architecture here. So this application runs on Google Assistant, which is the virtual assistant from Google, and it essentially runs on all devices that support Android, for instance. You can also download corresponding apps for iPhones, for instance. Here I'm going to demonstrate it on a smart speaker, but I'm also going to tell you which key phrase you have to say to your cell phones in order to access the demo that I'm making here. Alright, so now let's use the smart speaker. I can use the microphone, but I think it might be loud enough. You tell me if it is not loud enough, okay? Good. Okay, Google, talk to NYC Open Data.
Here's the test version of NYC Open Data. Ask about the New York City population. For instance, say statistics on visual impairment, or say who has difficulties with hearing in Jackson Heights. Say help for options.
Statistics on hearing disabilities.
Some facts on hearing disabilities. For the age group of 65 years and older, 100 out of 1,000 persons have hearing disabilities. It decreases to 11 for the age group of 18 to 64 years. It decreases to 6 for the age group of 18 years and younger. Say help or ask more.